Ow. You know how to take derivatives. You showed me that you can compute derivatives. That was the second exam. But apparently, once you've computed them, you have no idea what to do with them. And this bothered the hell out of me. I would also like to point out that the exam was eminently doable. That shift from having a center in the 70s to a center in the 60s, dropping everything this substantially. This is also common in most semesters. It's usually not 10 points, but it is usually 5 or 6. So having the average go from the mid-70s to the high 60s was what I was expecting. I will say I was happier, though, to see that the low came up. So y'all got closer together. This is a good thing, a smaller standard deviation than before. I will also tell you that I ran final grades. Everyone in this room, everyone in this course can still pass. No one's failed yet, period. Whether or not you can achieve the score on the final exam that allows you a passing grade, only you can determine. I want you to review this exam. You will see this stuff again. Guaranteed. Final's comprehensive. Meanwhile, I want to continue with my buddy Riemann. We're doing areas under curves. The area under F, between F and the x-axis, between A and B, is given by our Riemann sum. The xi star are the sample points chosen within each subinterval that we divide from A to B into n pieces, chop it all up, pick a point in each one, then we let the number of slices go to infinity. This symbol bothers me. And since we are taking the limit of a sum, that's sigma, the notation gets changed because you'll notice nowhere in this actual description does A and B show up. They only show up in our creation of delta x. I really want to tie this to being from A to B. So the notation was changed. And I'm going to write, instead of the sum, an elongated capital letter S. The sum, starting at A and ending at B. Of what? Of areas of little rectangles. Rectangles whose height is given by f of x and whose width is a small piece of the x-axis, a differential. This is the definite integral. And we're going to set this thing, this integral value, equal to this sum. The only requirement for f is continuity. And eventually, we will figure out how to relax that restriction. Now, that symbol has a bunch of pieces. We need to name them. The integral symbol, the integral sign itself. That's our elongated letter S. It's also the reason you get a lot of violins associated with calculus. It's an F hole on a violin side. We have a lower limit down here. We have an upper limit. We have the function inside. The function is called the integrand. And then we have our differential. That way you know what pieces I'm talking about when I refer to these things. But there's absolutely no requirement that I use x. Writing this let me find the actual example I'm going to do. The integral from 0 to 3 of the function x cubed minus 6x dx with respect to x is exactly the same as writing the integral from 0 to 3 of y cubed minus 6y dy. The letter itself is irrelevant. It's a dummy, a placeholder. I don't care what variable you want to use. One of my undergraduate professors routinely used to just mess with us and use whatever variable he thought would be the most amusing picture at the time. I don't care. As long as Stickman's a variable, we're good. These are all the same thing. Do me a favor. Graph the function x cubed minus 6x. I really only care about what's going on between 0 and 3, so we really only need to look at that part of it. What happens when you graph this function? Yes, but it isn't to start with at 0, is it? If I only care about what's going on between 0 and 3, I should change my x windows so that I'm really only looking between 0 and 3. And then I'll see the piece of this function that I'm interested in, and it looks like this. It crosses the x-axis somewhere between 2 and 3. But I have a problem when I look at this. Because when we were looking at our example, and in all of the pictures that we did last week, I looked at something that looked like that. And that function is entirely above the x-axis. And since I'm measuring the height of my rectangles by y values selected for my functions, all of those y values were positive in this picture. But now, some of those y values will be negative. My area actually is a signed area. When I do the integral that we are looking at, we're assigning potentially negative numbers to area. As a matter of fact, I'm going to subdivide this image and think of it as two pieces. I'm going to think of this piece down here and this piece up above the x-axis. And then I'll think of area is a positive thing. I don't know how to make a, didn't we say this when we were doing the garden against the house? I don't know how to make negative fence. I don't know how to make negative area. I'm not going to make negative area. I'm going to consider this area as positive, but assign it a minus value because it's below the x-axis. So really, when I think of that integral, I'm thinking of two areas. The integral from 0 to 3 of x cubed minus 6x dx is going to be a negative number plus positive number. I treat area as a positive thing, but its position makes it positive or negative. I've done this before. Matter of fact, you did it. We talked about gravity. What is the value of G in all of those motion problems that we were doing? It's negative. Whether it's 9.8 or 32, it's negative. You said down was negative. I'm saying the same thing. Anything that occurs under the x-axis is negative. We made it up. You could reverse that if you wanted to. We just have to make sure we are consistent in our decisions. Okay. I want to find this area. What do I do? If I'm following our definition here, I could pick a number of rectangles and guess. Get close, right? How many rectangles do you want to use? That's a legitimate question. Say again? 9. I'm going to use 9 rectangles. I'm going to put 3 between 0 and 1, 3 between 1 and 2, and 3 between 2 and 3. Means I got to write up all my division points. Okay. If I'm doing 9 rectangles, how wide is each one? Say again? Oh, careful. I'm going from 0 to 3, right? I'm doing 9 rectangles. It's right end minus left end divided by our number. That's 1/3, not a ninth. If I was going from 0 to 1, you'd be correct. I'm going from 0 to 3. Left end, right end, middle. How am I going to pick my xi star? I like being consistent, so I want to use the same one each time. But that's me being pedantic. We don't have to. Which one do you want to use? Left, right, or middle? Middle? Oh boy. Here we go. My picture sucks. That's okay. I don't need it to be perfect. This is the first rectangle. Its left edge is 0. Its right edge is 1/3. What's the middle of that interval? Add the two together, divide by 2. That's x1 star. Do the same thing for each. Of the 9 subintervals sitting here. So halfway between 1/3 and 2/3. 1/3 plus 2/3 divided by 2 is a half. If you use a common denominator, it's 2/6 and 4/6, and then the middle is 3/6. Between 4/6 and 6/6, the middle will be 5/6. And so on. I need all 9 of them. If I count by sixths, I'm going to add 1/3 each time I step, right? The width of my step is 1/3, so I can just keep adding 2/6. So I get 5/6 to 7/6 to 9/6, that's 3/2, to 11/6, to 13/6, to 15/6. Wait a minute, that simplifies. That's 5/2 to 17/6. Those are my 9 midpoints. That's disgusting, but it works. We're doing a middle, not a left or right, so I'm going to call it M9. The middle sum 9 rectangles. Height times width, height times width, height times width. I factored out the width, so I'm just adding up all the heights first. So I need a bunch of numbers. Here's my graph. I can put in all these numbers right here. But now, this becomes a giant arithmetic problem. So I put in, hit the trace button, I put in 1/6, and I get that number. Negative 0.9953704. I put in 3/6, 3 divided by 6. I get negative 2.875. I'm subtracting, well, I'm adding a negative. I put in 5/6, negative 4.421296. 7/6, nine sixths, 11/6, 11/13, 15. Oh, that's positive, so don't forget, we switch signs, 0.625. And 17. 5.7453704. And all of that, whatever I calculate that number to be, gets multiplied by what? 1/3. The width of our rectangle. A lot of arithmetic. I've come up with this answer when all is said and done. That's gross. Does this number make sense? Should my answer be negative rather than positive? Ah, this piece looks bigger than this one, so there should be more negative than there is positive, which means when I add it all up, I should end up with a negative answer. Okay, I'll buy this. It's not short. And this is just with 9 rectangles. I don't know what you're talking about. If I really want to do this right, I should do more rectangles and more rectangles and more rectangles, which means I need to do this at some point with like 900 rectangles. I think I'd rather hit myself in the head with a brick. So I'm going to cheat. And I'm going to do it once with n rectangles. And let n be a variable. And then we'll take a limit. Isn't that what our definition says do? Do a Riemann sum with n, and then take a limit. The problem is going to be figuring out how to write this crap. If there are n little subdivisions, I start at x0, the rightmost edge, which in this case is 0. Sorry, the leftmost edge. And I work my way to the right, step by step by step. On Thursday, we wrote up how to figure out what xi star was, based on whether we did the left, the right, or the middle. Out of those three options, the middle was the hardest. So I'm actually going to take that back, and I'm going to use the right endpoint. So let's use right endpoints instead. Okay. The first thing I need to know is how wide is each interval. That's my delta x. From 3 to 0, instead of dividing it into 9 pieces, I'm dividing it into n pieces. Now, look at that first subinterval all the way over there on the left. The right endpoint is x1. So x1 star is the same as x1. The second interval, the same thing is true. x2 star is x2. x3 star is x3. So xi star will be xi. So now I need to figure out what those numbers are. I start at 0. I move over one step. But one step is this width. So I moved over 1 times this. That's this value. What's x2? Relative to 0. I want a number for x2. x2 is what x value? It's one more step, right? So add another 3 over n. Or I could think of it as starting at 0 and taking 2 steps, right? So I can write it as 3 over n times 2. What's x3? Say it loud. 9 over n, or 3 over n times 3. If I keep going this way, what's xi? It's 3 over n times I. Now, this is actually really, really useful to me. Because what I have now is an expression that tells me this for every single box all at once. F of xi star is f of 3i over n. That's the x value I'm going to plug in to get a height. Every time. Not just once. I don't have to calculate a different value. I can try and write this as that Riemann sum. I have an expression that involves I. And we know what to do with an x. When we go to plug it into our function, what's our function again? Aha. Okay. Xi star is this thing. So this becomes 3i over n, all cubed, minus 6 times 3i over n. Delta x. We knew delta x also, didn't we? What was delta x? 3 over n. And now, a lot of algebra. I want to cube this. I'm cubing a fraction. When you cube a fraction, you cube the top, you cube the bottom. What's 3 cubed? 3 times 3 times 3 is 27. 27 I cubed over n cubed. I to the third, n to the third. Here I'm just going to multiply. 6 times 3 is 18 I over n. I still have a multiplication there on the outside, the 3 over n on the end there. Let's multiply that in as well. 27 times 3. 81. Three times 18. Okay. Yes, ma'am. Oh, I forgot to multiply by the n on the bottom. Got to multiply by the n on the bottom also. Thank you. I am adding up all of these numbers. But if I asked you to add and then subtract, couldn't you do the subtraction first and then the adding? Right? Do you see those parentheses? Those parentheses tell me to do the subtraction first and then add, right? So I don't know, I'm making up numbers. 5 minus 3 plus 7 minus 2 plus 19 minus 41. But you're just adding and subtracting, right? Can't you rearrange those as long as you keep the correct signs with the correct numbers? So what if I told you to do all the first numbers and add them up separate? Then do all the second numbers and add them up separate, and then subtract. That would still work, wouldn't it? I could say, oh, I'm going to do all the adding for the 81 I cubed over n to the fourth. And I'm going to do all the adding for the 54i over n squared. And then I'm going to subtract the totals. So rather than think of all of the debits and credits separately, I add up all the credits first, I add up all the debits, and then I subtract. balance my checkbook this way, right? At least I hope the checkbook balances this way. That sigma is a loop, right? It's repeatedly taking the I, which changes each time, right? So when I is 1, then I is 2, then I is 3, then I is 4, all the way up to n. Yes? Does the 54 ever change? Does the n squared on the bottom ever change? The only thing that changes is I. If I thought of this as a giant set of parentheses with things being added up, everyone would have a 54 on the top and an n squared on the bottom. Couldn't I factor it out of the parentheses? Which means I can factor it out of the sigma. The only thing that changes is I. So that's the only thing I need to keep track of within my loop. Same thing with the I cube here. Now here's the problem. And interesting enough, this problem goes all the way back to Greek antiquity. I want to add up the numbers from 1 to n. I want to add up the cubes of those numbers as well. I could just as easily ask you to add up squares or fourth powers or any power, right? I just picked x cubed and x because they were in my function. How the hell do I do this? An aside. I would like you to add up the numbers from 1 to 100 without your calculator. This was done in the classroom of grade schoolers. And the teacher figured they'd have enough time to go down to the restroom and come back. And sitting in the corner, student went, I'm done. Numbers from 1 to 100 add up to 5,050. How did you get that? Nope. 1 to 100. They're definitely not prime numbers. Hey, you're starting to wave in the back there. What's going on? No? Think about the line going from 1 to 100. And we're adding them all, right? I can rearrange them. Let's take the first number and the last number. What do they add up to? Let's take the second number, the next to the last number. 2 and 99 add up to 3 and 98, 4 and 97. They all add up to 101, don't they? How many times? I took my list and I divided it into 2 pieces, the high number and the low number. So each number got paired with something else. How many pairs do I have? The 100 numbers, I have 50 pairs. 50 times 101 is 5,050. I'm done. As a matter of fact, this is true for every number n. The first number and n add up to n plus 1. 2 and n minus 1 add up to n plus 1. And I can pair them all up. This total is n pairs, each with a value of n plus 1. You'll notice what's missing from that answer. There's no I anymore. I added them all up. That's the total. You want to go from 1 to 1,000? You take 1,001 and multiply by 500. You're done. N plus 1 and n over 2 pairs. And I can do it for squares and cubes and lots of other setups. Page 387 shows me those formulas. How I prove that these always work is actually something I'll do next semester in discrete math if you're interested. I didn't think so. A bunch of people are going, I don't want to know. Promise, it works. But page 387. But the bottom formula here is the sum for cubes, and that means I can actually work this one out. This one turns out to be the square of this one. Wait a second. Let me put those coefficients back on there. I'm sorry? What I can do is rearrange though, right? I'm just going to switch. Right, this one is 8. Well, I got to square all of this, right? Yes, ma'am. Unfortunately, it is just squared. Bottom of page 387. It's squared. There's a lovely inductive argument. It turns out that the sum of cubes is always a square. There's a geometry picture that goes with it. It's not in the textbook. I really wish it was. I'll find it and I'll post it to our Canvas page. 81 over n to the fourth, n squared, n plus 1 squared over 4. Minus 54 n plus 1. This is over 2. This is over n squared. I'm going to rearrange a little and write 81 over 4 and then n squared, n plus 1 squared over n to the fourth. And then here I'm going to write 54 over 2. I'm going to write n plus 1 over n squared. Please notice, if you want to do 9 rectangles, you can put 9 in for n. You want to do 100 rectangles? Put in 100 for n. You want to do 1,000 rectangles? Put in 1,000 for n. You found your answer. This is the area for Rn, the right-handed sum with n rectangles. But what do I want to do with n? I want it to go to infinity. So the area from 0 to 3 of x cubed minus 6x dx is the limit as n goes to infinity of this thing. Now I can hear in the back of your heads, that's not anything better. And you're right, it's not. That's gross and disgusting and does not look at all like we've improved it. Yes. My pen must have skipped. Wait a minute, this is a limit. Back to chapter 2 I go, searching through the memory banks. The limit of a difference is the difference of the limits. Hey, wait a minute. What's 54 divided by 2? 54 is even. It's got to be divisible by 2. And when I have a limit, I can take numbers that are inside the limit, outside the limit. Constants get pulled out. Now, all of a sudden, my brain lights up. And I go back to exam 1. And I go to the last question on the first page, which was about limits, as we went off to infinity. And these things are rational functions. Power of n on top, power of n on bottom. When we did it on the exam, it was x's. I don't care what letter you use. I can evaluate this limit. Because the highest power on top is n squared. The highest power on the bottom is n squared. I use the coefficients. It's 1n squared on top. It's 1n squared on bottom. That limit is 1. Multiply this out. The highest power on top is 1n to the 4th. The highest power on the bottom is 1n to the 4th. This limit is 1. Guess what? I'm done. I found the exact area, not an approximation, not guesswork. I found the exact area under that curve. In the longest way possible, absolutely. The longest way possible. By the way, if I had a geometric shape, like a part of a circle or a triangle or a rectangle, I could just use geometry. Midpoints are harder, but they still can be done the same way. I'm just going to have an uglier thing with eyes in it. It would be really nice if there was a nicer way to do that. There is no way I could pull it off. But on Wednesday, I want you to all come in having recently listened to Eminem without me. Trust me, come in Wednesday morning with the song in your head. I'll see you on Wednesday.